Good afternoon, Southminster scholars. Welcome back to our series on the exploration of planets as well as Earth, our solar system. Before we begin, I want to add another reminder, as I've done in the past, about this year's annual Superheroes Fund that we are doing for our hourly paid employees. We have over 380 of those persons who work diligently and daily on our behalf to provide us the lifestyle that we have come to enjoy at Southminster. As we've gone through this pandemic and are still going through it, our hourly paid super employees have been here for us each day. You'll find that they work in various departments and areas of Southminster, in the dietary area, in the dining area, in finance, on the front desk, in healthcare, home care, housekeeping, maintenance, life enrichment, marketing, security, transportation, and in our wellness center. They are all over the place, helping us in every way possible, devoting their friendliness, their talents, and their energies all to our benefit. Other than their hourly compensation, they receive no other compensation from us. As you well know, they are not tipped in any fashion. This is the only time of year when we can thank them for their generous energies on our behalf. They've put themselves throughout the year on our front line, regardless of their own personal lives or needs. They've left the safety of their homes and many times accepted financial hardship to take care of us. We've been able to stay at home, wear masks, not touch our face, wash our hands, and socially distance ourselves while they have been right next to us, putting themselves on the line. At this time of year, we need to show them our appreciation for all the work that they've done on our behalf. As a member of the Southminster community, we hope you will support these wonderful employees by contributing to the community fund. By contributing to the community fund, your gift is tax deductible. You will make your check payable to the community fund, and on the for line, you will put Heroes or Superheroes Fund. That way it will be so designated. It is important for these employees to know how much they are appreciated by us for their service, and this fund helps make it possible that these good people remain at Southminster. Now today, in our solar system exploration, we're going to look at the structure and behavior of atmospheres. Atmospheres across the solar system are diverse in composition and thickness, yet they are similar in structure. Wind patterns on the planets are well organized. Rotation of some of the larger planets lead to a number of zonal winds. Surface temperature is a product of the atmosphere's composition. Nonetheless, human activity is also affecting Earth's atmosphere and climates, with the potential for long-term consequences. An exploration of Mars is on the horizon. Global warming could global warming make it possible to sustain life and make it hospitable on Mars? Dr. Summers will describe the atmospheric conditions and makeup of Earth, as well as the other planets in our solar system. Join with me today in enjoying this video.
I would like to start today with an amazing image taken by the Apollo 12 mission. This is an image of a solar eclipse, but it's not by the moon. This is the sun being eclipsed by Earth. The Apollo 12 mission flew through Earth's shadow and was able to get this amazing picture. Now, I note that this picture was not staged. They didn't really have to change the mission profile in order to get this picture done, because the Apollo missions were generally done during full moon. So the moon was at opposition, and flying through Earth's shadow was not really a detour. Now, it's a beautiful image, but what excites me is looking at that thin crescent of Earth's atmosphere. It's even exaggerated a bit by the backlighting. And it helps me appreciate what a thin blanket Earth's atmosphere really is. It's just a tiny margin that separates us from space. And in this sort of an image, it seems so fragile against all that empty blackness of space. And it's especially so because within that protective layer exists all the life we know of in the universe. On our 13,000 kilometer sized planet, just a 100 kilometer thick air bubble is where we exist. So let's take a closer look at that atmosphere and the other atmospheres across the solar system and how they are structured, how they behave, and how they affect the prospects of life. Our atmosphere on Earth consists of 77% nitrogen, 21% oxygen, 1% water vapor, and 1% argon. Now, this is not what most folks expect. Oxygen is not the main component of our atmosphere. Rather, nitrogen is. And nitrogen is not something we really think of much. Maybe we think about spreading some nitrogen in our garden, but it really is all around us in the air. Another surprise from a lot of people is that carbon dioxide is not an important constituent. For all that one hears about carbon dioxide as being a greenhouse gas, it's really less than 1/30th of 1% of our atmosphere. In contrast, Venus has plenty of carbon dioxide. It makes up 96% of Venus's atmosphere. The other 3% is nitrogen, and then there's some minor amounts of water vapor and argon. Venus has a much thicker atmosphere. The atmospheric pressure at the surface of Venus is about 100 times that of atmospheric pressure at the surface of Earth. Earth's atmosphere, in turn, has about 100 times the atmospheric pressure of Mars's atmosphere. Mars has a very thin atmosphere, but it's also mainly carbon dioxide, about 95%, with nitrogen and argon. These bar graphs summarize the compositions of these atmospheres, where you can see strongly that Earth is the odd man out here. Whereas Venus and Mars are dominated by carbon dioxide, Earth is dominated by nitrogen and has enough oxygen for us to be able to breathe. Another way to look at the atmospheres is through their vertical structure. We say that Earth's atmosphere is about 100 kilometers thick. But really, how do you measure the top of an atmosphere? Earth's atmosphere has 4 different levels: the troposphere, the stratosphere, the mesosphere, and the thermosphere. The troposphere extends from the ground up to about 15 kilometers, and it contains 80% of the mass of our atmosphere. It is dominated by heat absorbed by the ground and re-radiated. So the temperature decreases a few degrees for each kilometer you go up in height in the atmosphere. You've been through the troposphere because if you've taken an airplane flight, airplanes fly at about 10 kilometers, and that's about 2/3 of the way up the troposphere. Above the troposphere is the stratosphere, and in the stratosphere, ozone molecules absorb the ultraviolet radiation of the sun, and that causes the atmosphere to heat up. That continues on up to about 50 kilometers, which in there we encounter the mesosphere, and again the temperature then starts to decrease with altitude. That continues up to about 85 kilometers, where we hit the thermosphere, and the temperature then starts to increase with altitude because the atmosphere is absorbing the high energy radiation from the sun. The thermosphere includes the ionosphere, the electrically charged region where we see the auroras. Now, the height of the atmosphere, we say, is about 100 kilometers. Now, that's almost the top of the mesosphere, but not quite. Actually, here's a secret for you. It isn't really derived from the properties of the atmosphere. It basically was a calculation as to what is the highest altitude a plane could fly. And it's the boundary between what you would call aeronautics and astronautics. And they got a number around 100 kilometers, and they rounded it off to 100 kilometers because it's a good, honest number. And so you are not officially an astronaut unless you've crossed the 100-kilometer barrier. Here is a graph of the atmospheric temperature with height. And the blue line here is that of Earth's. And you can see how it decreases through the troposphere, increases through the stratosphere, decreases again through the mesosphere, and increases in the thermosphere. We can compare these regions to those on Venus and Mars. For Venus, we define the same levels, but you can see that the troposphere, the region where it's decreasing with temperature, goes up much, much higher. It goes up to about 65 kilometers. Now, I've heard the region on Venus between 65 kilometers and 95 kilometers called both the stratosphere and the mesosphere. So I'm not really sure which to call it. We'll just call it the middle atmosphere. And then the thermosphere begins around 95 kilometers. And so while the atmosphere of Venus is 100 times heavier than that of Earth, its height is about the same, 95 kilometers versus about 85 for Earth. And surprisingly, the same is true for Mars. Its upper atmosphere starts at about 110 kilometers, its middle atmosphere extends down to about 45 kilometers, and the lower atmosphere goes from there to the ground. For three atmospheric pressures of vastly different scales, it is surprising that they have roughly similar vertical extent. Also similar and surprising is the atmosphere of Saturn's large moon, Titan. Here's an image of Titan with it being backlit by the sun, somewhat like that solar eclipse image I showed you. And it's surprising, first of all, that Titan even has an atmosphere. The other moons are the same size, Ganymede, Callisto, Europa, our moon, as well as Mercury, which is smaller, by the way, than Titan. They do not have atmospheres. Secondly, it's surprising that its atmosphere extends to about 600 kilometers away from the moon. This is 6 times the extent of the atmospheres of the rocky planets. And third, it's surprising that for a moon, its atmospheric pressure is 1.5 times that of Earth. Now, considering the wide range of pressures on Venus and Mars, this sort of counts as a similarity as well, because Venus is 100 times larger and Mars is 100 times smaller, so being only 1.5 is really quite similar to Earth. Another similarity is that it is predominantly a nitrogen atmosphere. It is 98% nitrogen and about 2% methane. Methane reacts with the sun's ultraviolet radiation and forms a very dense smog layer high up in Titan's atmosphere. This is why you can't see through it. What you are seeing in this yellow region over here on this image is the smog layer high up in Titan's atmosphere. The Huygens probe that landed on the surface of Titan could not see the sun. So finally, out in the solar system, we have found worse smog than exists in Mexico City or Los Angeles. A couple other moons have a rather tenuous atmospheres. Io has an atmosphere that derives from its volcanic emissions. It's basically sulfur dioxide that has been spewed out by the volcanoes, or actually sublimated from the surface after the volcanic spewings condense on the surface. It is 1/billionth the pressure of Earth, and even that is lost to space relatively quickly. If you could suddenly turn off all the volcanoes on Io, eventually its atmosphere would disappear. Neptune's large moon, Triton, has an atmosphere of nitrogen and methane, just like Titan. Triton is like Titan. Sometimes you get those words mixed up. However, Titan's atmosphere is over 10,000 times more dense than Triton's. Triton is a very, very thin, wispy atmosphere that rises about 10 kilometers above its surface. Pluto's atmosphere is essentially the same as Triton. And due to its elliptical orbit, Pluto's atmosphere isn't permanent. It will actually freeze out as it gets further from the sun. Now, the New Horizons mission is headed toward Pluto, and it will arrive there in 2015. I hope there's enough atmosphere left that they can study it when they get there. The giant planets have deep atmospheres of hydrogen and helium, and they descend down to very high temperatures and pressures. And so instead of asking where's the top here, you can also ask where's the bottom? Well, since there is no surface on these giant planets, the thickness is irrelevant. It goes down for thousands of kilometers. What really is relevant is that the atmospheres are a significant percentage of mass of the planet. On the rocky planets, the atmospheric mass is a tiny, tiny percentage of the total mass of the planet. But here in the gas giant planets, it's a significant percentage. Now, as with the discussion of their interiors, Jupiter and Saturn fall into a little different category from that of Uranus and Neptune. Here are the temperature curves for Jupiter and Saturn. The 0 point here, I will note, is arbitrarily set at the pressure of 0.1 times Earth's atmosphere, and the y-axis shows you the altitude in kilometers above or below that arbitrary 0 point. The first thing you should notice is that these are very cold atmospheres. The temperatures on the x-axis are in the Kelvin scale, where 0 is the absolute 0. The degree range is the same as Celsius, but with water freezing at 273 degrees Kelvin. So if you take these temperatures and subtract 273 degrees, you get temperatures on the Celsius scale. The warmest temperatures on these plots are basically normal temperatures on Earth. And when you look at the tops of the atmospheres, they're about 200 degrees below 0. You see the same pattern as we saw for the rocky planets. The temperature decreases as you go up with height through the troposphere, and then it increases with height as you get through the thermosphere. The image here also shows the major cloud layers on Jupiter and Saturn. The different substances in its atmosphere will condense out at different temperatures and pressures. There are 3 distinct cloud levels in the atmospheres, one of ammonia ice, one of ammonium hydrosulfide, and one of water ice. So when you're looking at different clouds on Jupiter and Saturn, you're really looking to different depth and temperature within the atmosphere. For example, here's a picture of Jupiter from the Hubble Space Telescope. Note that it has many brown and white bands. Now the top is brown, and then you've got a couple brown bands up in the northern hemisphere, and some brown bands and a little bit of brown towards the South Pole. Contrast that to an infrared telescope image of it that sees the heat. When looking at the heat signature, those brown bands then become very bright in the infrared. What is happening is you're seeing deeper into the atmosphere and seeing higher temperatures through those brown bands. The brown bands are the lower clouds at higher temperature within Jupiter's atmosphere. These are the atmospheric temperature curves for Uranus and Neptune. The situation on Uranus and Neptune involves the same ideas we've already discussed, except we're dealing with even colder temperatures. You can see that to the depths we've probed in these two planets, the temperatures are still 100 to 150 degrees below freezing. And at their coldest, near the tops of the atmosphere, they're over 200 degrees below 0. This allows clouds that we would never see on any other planet, methane ice crystals, because methane doesn't freeze until minus 180 degrees centigrade. Here is an image that shows you these clouds. These are the white streaky features here on the planet Neptune. Note that the blue color of Neptune is also due to methane. Methane absorbs red light, and only blue light is reflected, and that gives Neptune its beautiful blue color. This reminds you a little bit of what we see on Earth. On Earth, we see blue skies with white clouds. This is visually similar, but physically it's entirely different. Earth's clouds, as you probably know, are made of water vapor. They occur at many different levels, but they actually have distinct levels. And again, if you've taken an airplane ride, you've probably noticed that sometimes you have to pass through the cloud deck, and it can be one type of weather beneath the cloud deck and a totally different type of weather up above the cloud deck. But there's a distinct level of clouds that you pass through. Also, Earth's sky is blue, because the air molecules are scattering blue light better than they scatter red light. Now, when you ask people, why is the sky blue? Sometimes they'll give you a crazy answer like, oh, because it reflects the water. And that's just wrong, okay? I just got to get rid of that misconception. If that were true, why would the sky be blue in Kansas, huh? When there's no water around. The sky is blue because the air molecules preferentially scatter blue light better than they scatter red light. All right. Now, Mars also has some wispy clouds. Here is an image of the clouds on Mars, and you can see them in the northern hemisphere up towards the North Pole, these very wispy white things. They have lower clouds that are made of water vapor, and the higher clouds that are cold enough to be carbon dioxide ice. Venus's clouds, well, I think Venus's clouds are probably the coolest clouds anywhere in the solar system. Because get this, they are actually made of sulfuric acid droplets. That's right, sulfuric acid clouds. How cool is that? They have a very thick cloud layer, about 50 kilometers up in the atmosphere. It's continual clouds for about 10 kilometers, a 10-kilometer thick cloud deck. So if you were on the surface of Venus, just like on the surface of Titan, you can't really see the sun. This also means that Venus is rather featureless when seen in visible light. The image I'm showing here uses ultraviolet light to sort of pierce through some of the clouds and be able to see the patterns in it. That sort of chevron pattern, you see this sort of Y-shaped pattern, all right, that leads us to our next topic, which is that of winds. And the basic idea for Earth and Venus is something we call Hadley cell convection. It's really simple. You already know it. It's basically hot air rises, cold air descends. Straightforward enough, right? Well, apply that to Earth. Where is it hottest? Along the equator. So hot air will rise at the equator. Where is it coldest? At the poles. Cold air will descend at the poles. So you have a simple natural circulation pattern from rising at the equator, streaming up to the poles, and descending at the poles. On Venus, it has a relatively slow rotation. Venus rotates in about 243 days, and that allows it to have one Hadley cell per hemisphere. This is a beautiful example of Hadley cell circulation. And then the winds, when you've got these circulation patterns going up, the winds, the jet stream on Venus, drive that chevron pattern. So take a Hadley cell circulation and then start to move it with jet stream winds, and you get that chevron pattern. I note that these winds are about 200 miles per hour. While Venus rotates in 243 days, the winds circulate around the planet in only 4 days. On Earth, we have faster rotation. And instead of producing one Hadley cell, we actually produce 3 cells. Near the equator, we're familiar with the trade winds, and they blow from east to west along the equatorial latitudes. At the mid-latitudes, such as that of most of the United States and Europe, the winds blow from west to east. And then the third cell, near the poles, again blow back in the opposite direction, east to west. I note that Antarctica has become a really great place for balloon-borne science, because you can launch the balloon, it will follow its winds all the way around the pole, and come back towards the launch area where you can recover it. In the US, we see these different trade wind motions in hurricanes. The familiar pattern is that a hurricane will form out in the southern Atlantic Ocean, it will move westward towards the US, it will turn up the coast, and move back eastward as it dissipates. It's born in the trade winds, and then it dissipates in the westerlies. The wind speeds on Earth, or in these hurricanes, level 1 hurricane is 75 miles per hour. They go all the way up to a level 5 hurricane, that's 150 miles per hour. On Earth, we have recorded wind speeds in excess of 200 miles per hour. Is that amazing? Well, no, not when you view it in the context of the solar system. Because the fastest speeds on Earth are equivalent to the 200 miles per hour jet stream that is seen on Venus all the time. And that's to say nothing of what we see on the giant planets. Jupiter is 10 times larger than Earth, but it rotates in half the time. Jupiter spins on its axis once every 10 hours. This produces a large number of zonal winds. These are the banded structure that we see in the planet. The lighter regions are called zones, and the darker regions are called bands. Like on Earth, one region is blowing west, and the region adjacent to it is blowing east, and the next one is blowing west, and the next one is blowing east. You can see from the image there are about a dozen or so of these regions. And sometimes we sort of think of these bands as permanent features, but they can change. Here are two images from the Hubble Space Telescope. And what I want to point out to you in the left-hand image, in March, you can see this white zone in the north. When we looked at it again in June, that white zone had become a dark band. Likewise, in the southern part of Jupiter, there's a sort of turbulent region that is dark in June, but looking back into March, it sort of had an inverted structure and a lot more calm in March. So while a tiger can't change its stripes, it appears Jupiter can. The wind speeds on Jupiter are relatively calm. Most of them are about 40 miles per hour, especially as you go towards the poles. The central band reaches about 200 miles per hour. Here is a plot of the Jupiter wind speeds with latitude. The x-axis is plotted in meters per second, but it is relatively simple. You can just multiply that by 2.2 and you'll get miles per hour. The fastest winds in the solar system are on Saturn. And here in comparison to Jupiter, it's the same plot for Saturn. And you can see where Jupiter's speeds reach about 200 miles per hour, Saturn's speeds reach 1,100 miles per hour. That's 5 times the maximum ever recorded on Earth. And this isn't just blowing once or twice. This is blowing all the time, every day. Now, when you think about the giant planets and wind speeds, it should bring up a question. Wind speed relative to what? On Earth, it's relative to the ground. On Saturn, it's relative to the internal rotation rate. However, recent Cassini observations have made us unsure exactly what the internal rotation rate of Saturn is. So although this is a record in the record books, we may have to put an asterisk next to it because it could be revised later. Still, no matter what we discover about the internal rotation rate, these winds are really fast. Now, when we look at Saturn, we can see that these winds produce the same banded structure that we see on Jupiter, although it's much more muted than we see on Jupiter. One unusual feature of Saturn is found at its poles. Remember how we had circular polar winds on Earth? Same thing appears on Saturn, but here it's in the shape of a hexagon. Don't ask me why. We just don't know. But you can see from this animation that it's a stable pattern. It was seen 30 years ago by Voyager and was seen again recently by Cassini. The situation on Uranus and Neptune is a little less clear because we have fewer observations. Uranus and Neptune have only been visited by one satellite, Voyager 2. Here are the winds on Uranus and Neptune. And you can see one thing that's interesting about them in comparison to Jupiter and Saturn is their equatorial jet streams flow west instead of flowing east. These jet streams are slower than their internal rotation period. The pole flow, as you can see, is more towards the east. Now, in preparing for this lecture, I looked up things on the internet. I found a lot of references that say Neptune has the fastest wind speeds in the solar system. And they were claiming 1,500 mile per hour winds on Neptune. And I couldn't reconcile it. And the only way I could reconcile it is if you look at Neptune and you take the peak of the eastward motion and the peak of the westward motion, if you stretch that, you could probably get on order 1,500 miles per hour winds. It seems that there was a press release in 1989 that quoted this as the measurement, but it ignores the internal rotation rate of Neptune. so it really isn't there. Neptune's strong winds produce that same banded structure, and it's, somewhat evident, like it's even subtler than it is on Saturn. On Uranus, if we just look with visible light, you don't see much. But if you enhance the image, and this right-hand image is the exact same as the left-hand image, but only enhanced, you can find the banded structure. It also shows up really well when looking in infrared. The last topic that I would like to discuss today is on the balance of atmospheres, specifically the heating and cooling. Here's an image that discusses the heat balance of an atmosphere. The atmosphere absorbs energy from the sun. Some light is reflected back by clouds. Some is absorbed by the atmosphere, like the ozone layer absorbs ultraviolet light. Some is absorbed by the surface, and then the surface re-radiates that energy in infrared light. Some of that re-radiated energy is also absorbed by the atmosphere, and some is radiated back to space. The major point of this balancing argument is that the inflow of energy from the sun must be balanced by the outflow of energy from reflection and re-radiation of that energy. If not, the planet will either be heating or cooling. Now, the greenhouse effect is the trapping of infrared radiation within the atmosphere. And the major molecules responsible for this are water vapor, carbon dioxide, and methane. The extra heat absorbed by these molecules acts like a blanket and keeps Earth's surface warmer. Here is that same temperature plot that I showed you before, but now I have an arrow here showing you where Earth's temperature on the surface would be if there were no greenhouse warming. Earth's average surface temperature without greenhouse would be minus 16 degrees Celsius, or 3 degrees Fahrenheit. The oceans would mostly be frozen. So a little bit of greenhouse warming is a good thing. Now, Venus is just a little closer to the sun, but because the amount of energy is proportional to the orbit radius squared, it actually absorbs twice as much energy from the sun as Earth. It has a 96% carbon dioxide atmosphere, which traps a lot of infrared radiation. So that caused the surface to heat up and heat up and heat up until enough infrared radiation could escape to balance the incoming light from the sun. This turned into a runaway greenhouse effect. And if you look, the surface temperature of Venus is way out here at 475 degrees centigrade. That's 900 degrees Fahrenheit. If you add in the fact that its atmospheric pressure is 100 times that of Earth, it is hot and dense enough to melt lead. The Soviet Venera probes that actually landed on the surface of Venus only lasted for about 20 minutes. Eventually, they probably just melted. And if you look at the plot, without a greenhouse effect, Venus would be colder than Earth. Now, we also have Mars plotted here, but its atmosphere is too thin. Even though it has plenty of carbon dioxide, it's too thin for much of a greenhouse. And its temperature without a greenhouse is pretty much the same as its temperature is with a greenhouse effect. So Venus is a caution. You can have too much of a good thing. So how does this relate to global warming? The point is that the Earth has about the same amount of carbon dioxide as Venus. But on Earth, most of it is locked up, mostly in the limestone deposits on the sea floor. If we look in the ice cores, we can sort of see how much carbon dioxide has been in the atmosphere for the last 400,000 years. Here is a plot from the Vostok ice core from Antarctica, and it shows the carbon dioxide record for the last 400,000 years has ranged basically between about 190 and 290 parts per million. Again, carbon dioxide is a very small part of the atmosphere, and here is its historical range. The low points correlate when Earth was experiencing ice ages, and the high points with interglacial periods. We happen to be in an interglacial period right now. If we look at a more recent historical record, we can see that over the last 1,000 years, there's a sharp spike in the carbon dioxide from the Industrial Revolution. And if we look at current data over the last 50 years, we show a continued consistent rise. The level is now 380 parts per million. This is the same jump since 1750 as from 1750 back to the last ice age. The big question that comes from this is, will the increased CO2 levels change the temperature of Earth's atmosphere? Evidence says that this is indeed happening. Here's a movie that shows you the sea ice at the North Pole over the last 20 or 30 years. It begins in 1979 and slowly steps through every year. You can see it growing and shrinking and growing and shrinking. And these measurements are made in September of every year, which is actually the seasonally smallest time for the sea ice. You can see in 2007 that it's quite small. Just to remind you, here's the sea ice in 1979, and here is the sea ice in 2007. It is the smallest ever recorded in September 2007. For the first time in history, the Northwest Passage above Canada opened up for a brief time. The trend has been downward, and if it continues, for in a few decades, the polar cap will melt completely during the summer. Now, the scientific evidence of global warming is real, but the atmosphere is a very complex system. There are a lot of feedback processes, but it's certainly clear that something is changing, and Venus shows us what a worst-case scenario looks like. On the other hand, how we react to this scientific evidence and what we plan to do about it is a social and a political issue, but I think it's something that we should seriously consider. I'll leave it there for today. And next, we'll talk about the weather. But not just any weather, some really serious extreme weather. We'll see you then.
you.